This is our central idea for topic 4.4. Gases in the Earth's atmosphere affect the climates that we see here on Earth. So we have to understand our atmosphere and what it's made out of, determine the temperature, the precipitation that we see in all of our biomes here on Earth. So for example, here in California, we're used to a very mild temperature, and we used to have fairly wet winters, although that's changing with changing direction or jet stream and which way moisture is being moved around the Earth. So we need to study the gases that exist in our atmosphere. And sorry about the very laggy. And we need to how they affect climate. So CO2 and water vapor, those are two things that we've mentioned before, both naturally occurring. And remember, the greenhouse, that's something that was here before, has been going on for a long time on Earth, thankfully. So basically, it keeps everything warmer than it would be without those gases. So in a real greenhouse, the glass or the plastic or whatever is, enclosing it keeps everything, the heat in. And for our planet, carbon dioxide and water vapor keep heat in. So we have a lot of CO2 in our atmosphere, and that's from cell respiration and the combustion of fossil fuels. So combustion is a fancy way of saying to burn. So burning fossil fuels, oil, coal, especially in this state, we're really big into natural gas. And there's ways we add CO2, and there's ways we can remove CO2 from the atmosphere. The principal one naturally is photosynthesis. So we have plants working not only on land but in the ocean to remove that CO2 from the air. And luckily for us, because we've been adding a lot of CO2 to the atmosphere lately, the ocean has been absorbing a lot of it, except that you get a lot of CO2 in the ocean, you increase pH, which you can imagine creates problems for a lot of different marine organisms. And this water vapor, you get a lot of evaporation from the ocean. Evaporation, especially near, where would you get the most evaporation from the ocean? Someplace warm, someplace hot. That place would be, starts with an E, equator. Okay, at the equator is where you get most of the water. So water is very good at absorbing and retaining heat. When it condenses into clouds, this heat is retained, so it kind of acts as a block, like a blanket. Okay, the heat tries to rise, it hits the clouds and stays down. And that's why it's cooler after a cloudless night. If you have that coverage, wake up, it's a lot warmer. So methane, it's really CO2, CO2, and CH4, methane, that we're really concerned about with global warming. There are other gases, but those are the main ones. They come from marshes. So it's a fancy way of saying swamps. And fossil fuel extraction. So when they go dig out natural gas or gasoline, sometimes coal too. Well, yeah, coal. There's methane release in those pockets where those gases come out at. And nitrous oxide is another one. N2O. Natural bacterial action, as we know our saprotrophs break down dead stuff, but also agricultural activity, which we should say N2O and methane, especially rice, which we have a lot of in California up near Sacramento. So, like we said before, greenhouse, natural, nothing wrong with the greenhouse. We like the greenhouse. Sun comes in under these short waves, gets re-radiated. The water, the methane, helps to block some of that heat and keeps it on in our atmosphere, and that keeps us nice and toasty. This, you might guess, is this enhanced greenhouse effect. You see more heat right here, and that's what's really disrupting our global balance. Why we're seeing these changes in our sea level, marine life is being affected, other life on land. Plants are blooming earlier in the spring, later in the fall. Animals are migrating differently because they don't need to go as far south as they used to because it's warm enough up in the north. Right about here is Yakima, where I'm from. This is Long Beach here. And the Central Valley area, these almonds, great place to grow almonds because of the warmth. Guess where they're starting to grow almonds now? You guess it, up in Yakima, all the way, Yakima, yeah, Davis High School, DHS, my alma mater. They're growing almonds up in Yakima now because it's warmer and it doesn't freeze as much. So that's kind of freaky for me. So this is a human enhanced. You can write that in, human enhanced. So less heat escapes out into space. More heat with the natural, less heat with human enhanced. So the gas, it's absorbing this long wave radiation, and the fancy word is infrared. Fancy way of saying heat. You may have seen night vision glasses, night vision goggles, night vision cameras. They're looking at infrared. They're looking for heat. So how it absorbs, and so this is concentration here. So how much is in the atmosphere? Now remember, CO2, for example, is 0.04%, which is pretty low, okay, especially compared to oxygen, it's 21%, or nitrogen, that's 78%. So it's low, but it has a big impact, 0.40. And methane has a greater ability to trap heat compared to CO2, but it's at lower concentrations. I can't remember offhand what that concentration is. But this concentration, for a great deal, depends on how quickly it enters the atmosphere and how slowly it breaks down. I think methane has it's like a 3 to 4 year lifespan. So here we have a nice little overview of what's happening. We do get some greenhouse gases from volcanic activity, but not nearly as much as we get from fossil fuel. A lot of people say, oh, it's the volcanoes creating that extra CO2. We don't know if it's human. Well, we do know. We can measure exactly how much we're making, can measure exactly what's coming out of these volcanoes. We as humans are very good at this. We have satellites and other methods of measuring this right here, and we know. And then you can see like cryosphere, you can see that reflects the light out into the atmosphere. and therefore prevents it from turning into heat on the ground. So check it out. We have this sunlight coming in. A lot of it is reflected by the atmosphere. Also reflected by the clouds. So just the air molecules themselves reflect some of that light. Clouds reflect some of it, and then a lot of times it gets to the surface, you also have it being reflected. What surface is best at reflecting sunlight? Something very bright, and that would be our ice caps. So like the ice caps. And if we're decreasing the ice caps, then we're going to have more heat being retained at the Earth's surface. And then this is the problem right here. There's more of this heat being released if we have less of that reflection. But still, the heat going out used to be radiated to space, but remember, more of this is coming back in and then heating our atmosphere up. So the sun is short wavelength, and the re-emitted radiation is longer wavelength. So you see 400 nanometers versus 10,000 nanometers, so much longer wavelengths. And here's something a lot of you will be taking TOK soon, theory of knowledge. Wavelengths, electromagnetic energy. How can we teach better? How can I teach you better, basically, about what wavelengths mean, what the electromagnetic energy is all about? Because in some of this, to understand global warming, you need to understand, the electromagnetic spectrum. Electromagnetic spectrum. So, radio waves are part of that. You got radiation, like X-rays. I think you've heard of gamma rays before, probably. I know you've heard of microwaves. And then, of course, the light spectrum. You've heard of UV. That's a UV. Okay. So there's a lot out there that we don't see. Like if you take the United States, Florida, well, that's pretty good. And you stretch the electromagnetic spectrum across. I think we saw this in Earth from Space. This is the whole electromagnetic spectrum. Well, we can see it's just like a penny right here. So there's all this electromagnetic spectrum that's influencing our life. So if you go back to that diagram that we just saw, atmosphere 6%, reflected by the clouds 20%, surface reflects 4%, so that adds up to 30%. So around 26 to 30% is absorbed or reflected before it even gets to the surface. Okay, anything that does get to the surface is mostly converted to heat, except for that 4% that gets reflected off the ice. Remember, that's a lot less now, maybe 3%. I'll look into that because this number is probably 10, 15 years old. So yeah, some is reflected back from ice caps. And so if you look back at that diagram, so about 70 to 80% of this energy absorbed by greenhouse gases remains in our atmosphere to further heat up. But without this greenhouse effect, we'd be negative 18 degrees on average, which that's pretty cold. We want to stay well above that. So this is something we worked on in class. So here you have Earth, here you have the atmosphere, the sun. So sun waves come down, short wavelength. We got a long wavelength. Boom. Bouncing back down. Boom. 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 Now some of it's going out to space. We'll say this is heat captured in atmosphere by CO2, methane, and Ooh, water vapor, H2O. Oh, hopefully that came through. Make sure you label this atmosphere. Might want to put in, you know, there's water in there, CH4, CO2. And then here we have, oh yeah, UV light, visible light, that's what we're seeing. In infrared, that's what you can't see, but a camera can get that. So what wavelength does CO2 absorb best? So we look at carbon dioxide, look right here. This is the wavelength right here, okay? So 10, this would be 100. So, sorry, I want to look at wavelength down here. So, right down here, so this is 10, right here is 20. So right between maybe like, a little bit more, like 17 micrometers. So 17 micron. Remember, micron is 1 millionth, 10 to the negative 6 meters. And let me see, do any greenhouse gases, let me look. Oh, absorb at 0.4. So let's look at this. So we're looking here 0.2, this would be 0.3, this would be 0.4. So let's go up here. Do you see anything? No. So there's no, so we put no, nothing at 0.4 microns. It's microns, right? Yeah. So that's our visible light. So it's not going to do much, but remember this infrared, this heat, water vapor especially, check it out. Water vapor, really good right here. And that would be like 7 microns. Methane, probably biggest right here, which would be 8 microns. Oh, okay.